Okay, let me talk about Taylor series. For an analytical function, we can write a function in terms of infinite polynomial, order of polynomial in this form. So an can be written as the nth order derivative at point A over n factorial. So let's not worry about this. I'll talk about this later. And to illustrate the point, I will make an example. Try to expand e to the x around x equals 0. As we know that whichever order of derivative of e to the x exponential is exponential itself. So this. We know e to the 0 is 1. So we have, remember this formula? We have e to the 0, so it's 1, and then this is this, and then it's 1 over n factorial. And the function can be written as sum from n to the 0 to infinity x to the nth over n factorial. To expand it, we can write into 1 plus x squared over 2 plus x cubed over 6, and 3 factorial is 6, and it goes on. It goes on, and we can plot it. The white line is e to the x. The yellow line is 1, and the red line is 1 plus x. So the 1 is the first order, only including the first term, and the red line is including 2 terms. The first term only works right at x equals to 0, but adding another term, it works pretty well around a certain small section around x equals to 0. If I add a third term, it works even better around x equals to 0. So with more term added, you'll find the function will look more like e to the x. And for someone who are interested in it, Frobenius series, you may not heard of it, but I think it's good for you to know it because it's very, very similar to Taylor series, but instead of x minus a to the nth power, you have n plus k power. K could be negative, so sometimes you will encounter like something like that. It could express some function that has a certain pose or certain at some point it will go to infinity, positive or negative infinity, and it can express that, and it's a very powerful tool. Just adding a little k here, and this method will be used all the time in solving differential equations. And also, I think if you modify this formula to this one, you could also use that for doing a good approximation of a certain function.